Let's do another problem here. Another example of applications of exponential functions. Let's do this computer depreciation problem. It says the value of a computer n years after its purchase is given in this table. So just studying the table, we see that 1 year after its purchase is 1200, 2 years is 960, 3 years is 7, and so on and so on and so on. So part A says determine whether it's linear, quadratic, or exponential would model the data most appropriately, and then determine the equation. So let's just do some quick checks here. Prove it's not linear. So if it was linear, 960, we have to do the first differences. And 960 subtract 1200. If it was linear, has to equal 768 subtract 960. So if we just do 960 subtract 1200, we get, and I'm just going to jot it down over here, we got negative 240. And if I do 768 subtract 960, I get negative 192, which is not the same, and it's even more different when I do 614 subtract 960, which is negative 346. Let me just jot all these down here. Let me move this table over. So this was negative 240. This was negative 192, and then this negative 154. Not the same at all. Now, so that rules out linear. If it was quadratic, the differences here, the second differences would be equal. Let's just do a quick check there. So if I take negative 192 and I subtract negative 240, I get 48. And if I do that here, this has got to be 48 if it's going to be quadratic. So I'll do negative 154 I get 38. So that's not the same. So I'm going to erase those now. And to prove it's exponential, the ratios between successive y's have to be the same. So 960 divided by 1200, I get 0.8. And if I do 768 divided by 960, I get 0.8. And you can verify that you'll get 0.8 all the way down. Since all those ratios are the same, this is exponential, and even more so, we know that this is the growth factor. So in our equations, a times b, let me just jot this down. So in our normal y equals a times b to the power of x, we know the b here is going to be 0.8. That common ratio is always the growth, or in this case, decay factor. It's going down. So let's come up with an equation here. Let's use v for value. So it's value based on n from the number of years after purchase. We'll need an a value, but I'm going to fill that in a minute. But we now know that the b value is 0.8, and this is happening every year. So we'll put an n up there. So now we have to determine the a value, which is our beginning value, like our y-intercept. Our y-intercept occurs when we have our independent variable being 0. So this is 1. So the 1200 is not the number that goes here. We got to put a 0. Like go back in the table at 0. That's the number we're looking for to be our y-intercept. So if we're we're basically, you take 1200, you multiply by 0.8, you get that. You multiply by 0.8 and 0.8 and 0.8 and 0.8. So I'm going to divide 1200 by 0.8 to go back in the table. And I get 1500, which means that's the original value of that computer. So that's our starting value. So there's our equation.